Let's learn about one concept that breaks every beginner. Recursion. Your computer needs to find every file buried in nested folders. You might think, just write a loop, right? But here's the problem. You open a folder. Inside, you find files and more folders. You open one of those folders. More files. More folders. You keep going deeper and deeper. How many levels deep? You don't know. A loop needs to know when to stop. It needs to know how many times to repeat. But when folders can nest infinitely, a loop gets stuck. It can't handle unknown depth. Watch what happens when we try. The loop opens the first folder, counts the files. Then it hits a subfolder and freezes. It doesn't know how to dive deeper. This visual representation highlights the conceptual challenge. The unknown depth of nested structures. A loop cannot determine how far down the hierarchy it needs to go. The loop's inability to proceed is directly linked to this lack of information about the structure's extent. It's like trying to explore a maze when you can only walk forward 5 steps. If the maze is 6 steps deep, you'll never reach the end. This is the limitation of loops. When structure is unknown, both the maze and the folder hierarchy demonstrate the same fundamental problem. A predefined limit prevents full exploration of an unknown or variable structure. But what if a function could call itself? What if, every time it found a subfolder, it just asked itself to solve that smaller problem? That's recursion. When a subfolder is encountered, the same countFiles function is invoked again, but for this specific subfolder. This creates a chain of function calls, each one handling a deeper level of nesting. This structure is known as the call stack in programming. Recursion efficiently manages this dynamic depth, providing an immediate solution where a loop would fail. The recursive calls naturally map to the folder's hierarchical structure, with each function instance addressing a specific level of depth. Once the deepest subfolder is processed, its file count, here 2 files, is returned from that function call. This result is then used by the calling function at the next level up, which adds its own file count to the received value. In this case resulting in 5 files. This aggregation continues up the entire call stack, with each function passing its total count to the one that called it, until the final count of 18 files reaches the topmost level. So what is recursion, really? It's a function asking itself the same question about a smaller version of the problem. Instead of solving everything at once, you solve one small piece, then trust the function to solve the rest. Let's see this with our file system. The function opens a folder. It counts the files it can see right now. That's the easy part. But then it finds subfolders. Instead of panicking, it just says, I'll call myself on each of those subfolders. Each time the function calls itself, the problem gets smaller. One folder becomes one subfolder. That subfolder might contain another subfolder. Keep going until you hit a folder with no subfolders inside. That's called the base case. It's the stopping point. Without it, the function would call itself forever and crash. But with it, recursion works beautifully. The base case says, if the folder is empty, return 0. This is the explicit condition that stops the recursion. Now the results are aggregated. The recursive case says, count files here, then add the counts from all subfolders. For the archive folder, we count its one file and add the 0 returned from old files, giving us a total of 1. Applying the same logic, the projects folder counts its 2 direct files and adds the 1 returned from archive, resulting in a total of 3. Finally, the original documents folder counts its 3 direct files and adds the 3 returned from projects, giving us the final total of 6 files. This demonstrates how the solution builds up from the smallest sub-problem. This step-by-step process reveals a fundamental pattern in how recursion works. Every recursive solution follows a clear structure, which we can visualize as a decision framework. The framework has 2 key parts: the base case, which defines when to stop and return a simple answer, and the recursive case, which handles the larger problem by solving one piece and calling itself on a smaller version of the problem. This loop continues until the base case is reached. Once you understand this pattern, you'll recognize the power of recursive thinking everywhere, allowing you to solve complex problems elegantly. Now let's see what actually happens in memory when recursion runs. Every time a function calls itself, the computer creates a new space in memory called a stack frame. This frame holds the function's variables and waits for the next call to finish. The frames stack up, one on top of another, as recursion dives deeper. This entire structure is called the call stack. Let's watch this happen with our file system. We start with the top-level folder. A function call is made for documents, and its corresponding frame, holding its specific variables, is added to the bottom of the call stack. The function then calls itself on the projects subfolder. As recursion dives deeper, another frame is added on top of the previous one, visually showing the stack growing and representing a new layer of execution. This process continues, with the function calling itself on the archive subfolder, adding yet another frame to the stack. We keep stacking up these frames, representing nested function calls until we hit a base case. Here, the archive folder has one file and 0 subfolders, which is our base case for this specific scenario. This function has completed its work and is now ready to return its calculated result, which is 1. Now the stack begins to unwind. The result of 1 from archive flows back to the project's function that called it. This function then adds its own files to the received result, performing the calculation 2 own files plus 1 from archive equals 3 and arriving at a total of 3. The result of 3 from projects then flows back to the initial documents function. After incorporating its own files and the results from other subfolders, the documents function finalizes the total count as 16. This demonstrates how the call stack grows downward as we dive deeper into recursion, then collapses upward as results bubble back to the initial call. Understanding this dynamic process is key to grasping how recursion manages its execution flow. The call stack is why recursion uses more memory compared to iterative approaches like loops. Each function call requires a new stack frame, consuming valuable memory space. If recursion goes too deep, you can run out of this dedicated stack space, leading to a critical error known as a stack overflow. This visual clearly illustrates that every single call in a recursive sequence adds to the memory footprint. The deeper the recursion, the more memory is consumed, pushing the system towards a potential overflow state. While recursion can be an elegant solution for certain problems, its memory usage can be a significant drawback. Iterative solutions, often implemented with loops, typically maintain a constant or minimal memory footprint, making them more efficient in terms of memory consumption. Therefore, when choosing between recursion and iteration, it is crucial to consider the potential for deep recursion and its impact on memory. Understanding this trade-off is essential for writing efficient and robust code that avoids performance issues. So when should you use recursion? Ask yourself, does the problem have a natural recursive structure? Is it nested, tree-like, or self-similar? Can you define a clear base case that's simple and reachable? Can you express the solution as solve one piece, then recursively solve the rest? Is recursion depth reasonable? Is recursion clearer than iteration? If yes, recursion is your tool. Our file system is a perfect example. Folders contain folders. The structure is inherently recursive. Recursion mirrors the problem's shape. But recursion isn't just for file systems. It's the language of trees and graphs. Binary search trees, depth-first search, parsing nested data like JSON, all of these rely on recursion. Mastering recursion unlocks entire families of algorithms. Divide and conquer algorithms, like merge sort and quicksort. Recursion. Backtracking algorithms for puzzles and games. Recursion. Once you understand recursion, You see it everywhere. It's not just a technique. It's a way of thinking. Break the problem into smaller versions of itself. Trust the function to solve the smaller problem. Combine the results. That's recursion. And now, you've got it.